is the review for limits. So before we start anything, I'm going to go over what a limit actually is. So a limit is essentially what the point on a graph or in an equation would be about. It's not, it doesn't have to be exactly, but it's what it would be about. So I'll give you a real life example of this. So if you have a wall here and you're standing here, okay, you go, little smiley face, right? You see your distance from the wall is this, right? So now if you wanted to take half your distance, you'd be here. Take half your distance again, you'd be here. Take half your distance again, you'd be here. Take half your distance again, you'd be here. And if you keep halving it, halving your distance, I mean from the wall, you'll never actually get down to the wall, right? Because obviously you can't have like all the way down because that's just physically impossible. So the point of a limit is to say that although you're not at the wall exactly, you're so close to the wall that it can be considered that you're at the wall. So if you're within the 0.00001 meter of it or whatever, that's where limits would come in. You would say you're at the wall. So where can this be used for math? So I'm going to erase this and I'm going to show you the first type of limit question. So the first good one is when you're given a graph, 1, 2, y. Okay, so there's the graph for the equation and for the question here. So there's a few questions that can be asked when you're looking at the graph. You can have a question like, what is the limit when x approaches 1 from the positive direction? And I'll go over what all this means in a second. I'm just writing them out. So these are the 6 main questions that you could be asked. You know what? I'm going to throw in one more just to start with. Okay. So we're going to start here where it says limit as x approaches 1 from the positive direction. So let's just go over what everything means. LIM for limit. So the limit as x. So we're looking at our x-axis. Approaches, that's what the arrow means for limits. 1, so where 1 is on the x-axis, that's where we're looking. So then what's the last thing mean? The plus sign, it means when x approaches 1 from the positive direction. So obviously this is the positive side, this is the negative side for x, right? Because infinity would be over here and negative infinity would be over here. So we're going to start on the right side. We're going to work our way this way. So we're going to follow along the graph, right? Go, 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 go. Oh, when you reach x equals 1, that's where you want to stop because that's where it's asking. As x approaches 1 from the positive direction. So now the question is when we're at 1, what are we going to put for that answer? Well, as I said before, for limits, it doesn't matter what the actual value is. It's what it's about to be. So although you see here, we have an open circle, it's still going to be considered 2 here. Because although you don't actually get to this value here, you're so close to it when you approach it from the positive direction that it's considered to be at that value. So that, again, that's the whole point of limits, is that although you're not actually going to get there because it's the open circle, it's so close that that's going to be your answer. So let's do the same thing for limit for x approaching 1 from the negative direction. So again, we have our negative direction here. So we're going to start, go, 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 go. You get to x equals 1. Okay. So now what are we seeing here? We see that as x gets close to 1, we see that the y value is about 1. So our answer here is going to be 1. again, for the first one, we came from the positive direction, and it's, even though it's not actually 2 when you plug in for, and we'll see that for when we plug in for f of 1, although it's not actually at 2 because the open circle, for limits, you say that the answer is 2 because it's so close that it's going to be considered it. From the negative direction, it doesn't really matter, but it's the same thing. If this was an open circle, the answer would still be 1 because although you're not actually there, you're so close to it. So the next question where it says the limit as x approaches 1. In order to do something where it doesn't have from the positive or from the negative direction, you have to check both the positive and negative direction. If the positive and the negative directions are the same, that's same, are the same, then it's that value. If not, it does not exist. Now, there's a few exceptions to that that I'll go over later, but that's the general rule. So if you see something that just asks for what the limit is for a certain number, you have to check for from the positive direction and from the negative direction. If those are both the same, then whatever that value is your limit. But if they're not the same, then the limit does not exist. So we did this for 1. So when it approached from the positive direction, when x approached 1 from the positive direction, it equaled 2. And when x approached 1 from the negative direction, it equaled 1. So obviously they're not the same. So this does not exist. So now we're going to go over here to the limit as x approaches 2. So let's start from the positive direction, going down, stop. So the value when x approaches 2 from the positive direction is going to be 2. The value when it approaches it from the negative direction is going to be also 2. So as you see, since from the positive direction and the negative direction, they're the same, the answer here would be 2. Why I threw that in there is just because although you see the gap in the graph here, it's not going to affect any points that are not x equals 1. So if you have a point here that's not near this gap, it's not going to be affected by it. And that's the whole thing. Don't let that throw you off. So let's get to the next one, f of 1. So this is what you did before. So all you're going to do is you're going to look at x equals 1. But instead of taking the limit, you're actually going to take the real value for when x is equal to 1. So obviously, you're not going to take it the open circle because the open circle means that it is not quite there yet. So you're going to look for the closed circle. So when x equals 1, y equals 1. You'll notice that's the same thing as when you approach it from the negative direction because it's on the same line here. That's not really too bad. The limit as x approaches infinity. So infinity, as I said, was over here. Oh, that's a terrible infinity. Infinity was over here. Negative infinity is over here. So as x approaches infinity, so we see the lines going up and up and up, and we can just imagine that it's going on forever. So what's that going to be about? It's going to be at infinity because it's going to go up and up and up forever. As x approaches negative infinity, it's going down, 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 down. Where's that going to be? It's going to be at negative infinity. If you had a graph that looks something like this, Pretend that's an asymptote. I know that's not very straight. That looks something like this. As x for the limit as x approaches negative infinity, you'd follow along the line as it approaches negative infinity, and it looks like that value would be 0. Right? So that's how you do it. You follow along and you think what would it be when it reached infinity or negative infinity? So that's the first easy type of limits. So now I'm going to go on to the second major thing for limits. And that is when you're given an equation. So I'll go through this quick. If you're given the equation, y equals 3x plus 2, let's say, and you're asked for the limit as x approaches, let's say, -1, okay? Notice how I don't have the from the plus or from the negative side, the positive or negative side. You just have to do that in your head. Remember, whenever you don't see the sign here, you still have to do both and you have to check them. But a trick that we can see here is that although we don't have the graph, we can visualize what 3x plus 2 is going to look like. So we can think of it like something like this. It's going to look something like that. Okay, -1 is going to be whatever, about here. But an easier way of doing that is the idea that whatever the f of x is equals the limit for x approaching whatever. Right? And that only works if it's a continuous graph. Now, what do I mean by continuous? I mean that there's no sudden jump. So like in the last graph where we had that closed circle, open circle, right? And they were like this, that is not a continuous graph at that point, right? Because there's that difference, right? There's that difference and it's not a continuous line, excuse me. So a good way of being able to tell that this is a continuous line is because first off, there's nothing in the denominator. So if this is only over 1, but if there's something in the denominator, then you need to check it a little closer. But obviously, since this is continuous, this is just a line, we can plug in whatever we're looking for. So -1 into the equation, 3 times plus 2, -3 plus 2, -1. So the limit as x approaches -1 is going to be -1. And again, the reasoning behind that is since this is a continuous graph, remember, we know it's continuous because there's nothing in the denominator, and we can visualize this graphically. We know that this is going to just be a straight line. Since it's a continuous graph, the value for f of x is equal to the limit for x. So the value for f of -1 is equal to the limit for x approaching -1. And when I say f of x, it just means you're plugging in whatever that value is into that. So let's get on to another type of limits. And that's going to be ones that are, let's see, are we doing ones that are approaching infinity and negative infinity, right? So you'll be given a graph like, let's start with and it'll say, what's the limit as x approaches infinity? So how do you do this? Well, obviously, this graph's going to be a little difficult to draw. But when you see something for infinity, you're not going to have to worry about it being continuous or not, because any breaks or asymptotes in the graph are not going to be that high. So you could just follow the same rules before where you're just going to plug it in for f of x. So let's just visualize this. If you have a number like infinity that's really, really, really big, it's difficult to quantify because obviously you can always get bigger than any number that I write out. So let's see, if you plugged in a really long number for x, so obviously, let's say like 10 million, 2 times 10 million plus 3, it's going to be like 20 million plus 20 million and 3, right? So we see that this 3 does not really matter in this case. It's only whatever is attached to the x. So we'll do the same thing down here. 10 million minus 4 is just going to be less than 10 million. So again, that doesn't matter. So we're just looking at these 2 leading coefficients. And that's a good general rule to follow, is that no matter what you see, whatever x's have the biggest exponent, that's what you want to be looking at. So the rule when the exponents for the x's are the same, because they're both 1 here, is you take the leading coefficients, right? Because we said up here it's going to be like 20 million, and down here it's going to be 10 million. So 20 million divided by 10 million is going to give you 2. Easier way to do that, 2 divided by 1 is going to give you 2. So that's the rule for if the leading, or for if the exponents for the biggest x value are the same. So let's see if what it's going to be like when it's different. Okay. Again, we got the limit as x approaches infinity. Okay. So we could just do the same thing that we did before. We know that since we're looking at infinity, anything that's not the biggest number in front is just going to completely cancel out. So the rule for when the exponent for the top, because we see the exponent here is 2 and the exponent here is 1, is bigger than the bottom, is that the answer is going to be infinity. And how do I know that? It's because if you plug infinity in for x, right? Let's say we stick with the 10 million. On the top, we're going to have 3 times 10 million squared over 10 million. And whatever that division is, it's not going to be anything in comparison to whatever this 10 million or infinity squared is. You see that if you're squaring it up here, it's going to have such a tremendous impact on it that dividing it by whatever is not going to have a big impact. So the rule for when, if that's difficult to follow, just memorize the rule. The rule for when the exponent's bigger on the top than it is on the bottom is that when x approaches infinity, the answer is infinity. I just want to say quick, if it said as x approaches negative infinity, you'd do the same thing, but instead of regular instead of like a large number like 10,000, you'd plug in negative 10,000 just to conceptualize it. So then our last case is going to be one where it's bigger on the bottom than it is on top. So this is our final rule. Obviously, we see that the exponent up here is 1 and the exponent down here is 3. So we see that the exponent on the bottom is bigger. So we're looking for the limit as x approaches infinity. So how do we do that? We can go and do the same thing that we were doing before, where we just plug in a tremendously huge number. Obviously, that's not infinity, but it works good enough for our purposes. So plug in something like 10 million, 2 times 10 million is 20 million, and then 3 times 10 million to the third. So it's going to give you some small number, relatively small number, over a massive number. Because you see, if you're plugging in infinity here for the x here that's being raised to the 3rd power, it's just going to be so much more massive than whatever this value is, because it's only being raised to the 1st power. So you have a really small number over a massive number. So think about it. If I gave you something like 2 over 100,000, whatever that decimal is going to be, it's going to be like 0.000 whatever. And the whole point of limits is that, as we said before, even though it doesn't actually reach 0, it's going to keep getting closer and closer to 0 the bigger that infinity is. So the rule for when the exponent is bigger on the bottom than it is on the top is that the answer for the limit of infinity as x approaches infinity is going to be 0, if you like just memorizing rules. So then the last case is when we have something like, let's see, how can I do this here? Then we have okay. This is our last case here, last special case. So we're going to do what we did before, and we're going to plug it in. So we're going to see 3 squared minus 9 over 3 minus 3. and we end up getting 9 minus 9 over 3 minus 3, and we get 0 over 0. Fine, that's what we did before. Whatever, same steps. The only problem here is that the rule for when you have 0 over 0 is that you can't have it. You have to do something in order to make it disappear and get the actual answer. So if you have something that's 0 over 0, it's considered indeterminate form. And as I said, that's for 0 over 0. That's an important term to know, because if somebody asks, what is the, why can't you have 0 over 0? You say because it's an indeterminate form, and you need to do something in order to manipulate the equation in order to get a different answer. So what can we do here? Obviously, if you couldn't tell, we can factor out the top. So we get x plus 3, x minus 3 over x minus 3. The first thing you should do whenever you see 0 over 0 is just try and factor one of them, because odds are is that one of them will cancel out, and that'll clear it up right away. So we see here that the top and the bottom are going to cancel out for x minus 3. So then you're left with x plus 3. And then now we can just plug in our 3 for x. 3 plus 3 equals 6. So our limit as x approaches 3 is 6. Simple enough. Let's see if I missed anything else. Let's just go over this. If you have x, just erase this. This is going back to what I did before. I just want to touch on something. Over as limit as x approaches infinity. So this is one of the questions we were doing before, where you got to look at the exponents for the leading, for the biggest x. So again, whatever's not the biggest term in the top and the bottom is irrelevant. It's not going to have a big impact on it. It's not going to matter for what we're looking at. So what do we do here? Now you might be tempted to just say, oh, I see a 4 here and I see a 2 here, so the top is bigger. So the answer is going to be infinity. But that's not the case, because you see that you have a square root here. So you can actually simplify what's on the top, and you end up getting the square root of 5 times the square root, it's supposed to be times, the square root of x to the 4th. And what is that? It's the square root of 5 times x squared. So you're left with the square root of 5 x squared over x squared. So now we see that in reality, the exponents are actually the same on the top and the bottom. And the reason that I bring this up is because a lot of people, when you're square rooting something like this, they'll either just follow that rule right away and they won't pay attention to that, or they'll just take the 5 and they'll mess up and they won't do a square root of 5. It is okay to have something like this, a weird number like this, because you're going to get that when you're square rooting that. So what's the rule when you have the exponents that are the same? Well, you look at the leading coefficients. So the leading coefficient here is 1. The leading coefficient on the top is rad 5. So whatever the top divided by the bottom is, so rad 5 divided by 1, so your answer is going to be rad 5. The biggest thing there is just knowing that you can have a radical. It's totally normal. And making sure that if you see a square root, you're not just going to immediately jump to anything without first trying to simplify it. I think I touched on everything. Okay, thank you.